Chain rule describes a rule for computing the derivative of a composition. Let's start with a relatively simple example. Suppose that f of x is 2x and g of x is 3x. Then the derivatives of f and g we know. They're just given by f prime of x equals 2 and g prime of x equals 3. But what about the derivative of their composition? Well, f composed with g applied to x is just f applied to 3x, which itself equals 2 times 3x, or 6x. The derivative of this composition is therefore 6. Since 6 is equal to 2 times 3, we realize that this derivative is just given by the product of the derivatives we found earlier. What this suggests then is that perhaps the derivative of the composition is equal to the product of the derivatives. It turns out that this is mostly correct, but there's one subtlety that we need to address. Let's look at another example to see why. Suppose that f of x is x squared and g of x is 2x plus 1. The derivatives of f and g are 2x and 2, respectively. From our previous observations then, we might guess that the derivative of the composition should be their product, namely 2x times 2, which is just 4x. But this turns out to be wrong. To see why, let's write out the composition. Since g is 2x plus 1 and f is x squared, f composed with g is given by the quantity 2x plus 1 squared. Now, to compute the derivative, let's expand out this quantity. Upon doing so, we find that it's equal to 4x squared plus 4x plus 1. And now we can take the derivative to find that it's equal to 8x plus 4. Notice that this isn't the product that we found earlier. In other words, 8x plus 4 is not equal to 2x times 2. Instead, this derivative is another product, namely the product of the derivative of f at the point g of x times the derivative of g of x. Indeed, the derivative of f is just 2x, and so this expression applied to 2x plus 1 is given by 4x plus 2. Upon multiplying this quantity by the derivative of g, which is just 2, we obtain 8x plus 4, which is indeed the derivative of the composition that we computed earlier. In summary then, the derivative of the composition is indeed a product, but the term involving the derivative of the outside function needs to be applied at the inside function. All of this is summarized precisely by the statement of the chain rule. Specifically, if f and g are both differentiable, then the derivative of the composition f composed with g is given by f prime applied to g of x times g prime of x. One way of thinking about the expression that appears on the right-hand side is by thinking of the inside function as just blah. Then, the derivative of the composition is given by the derivative of the outside function applied to blah times the derivative of blah itself. Let's do some examples to illustrate the principle. Here, we'd like to compute the derivative of sine applied to x squared. Notice that this is indeed a composition where the function x squared is applied to x, and then the function sine is applied after that. This means that we can use the chain rule to compute the derivative. Let's write f of u for sine u, which is the outside function, and g of x for x squared, which is the inside function. The chain rule says that the derivative is given by f prime at g of x times g prime of x. Here, f prime of u is just given by cosine of u, and applying this to g of x gives cosine of x squared. G prime of x is just 2x. In total then, the chain rule says that the derivative is given by cosine of x squared times 2x. Let's compute the opposite composition too for good measure. In other words, let's compute the derivative of the quantity sine of x all squared. Here, the outside function is the squaring function, f of u equals u squared, and the inside function is now g of x equals sine x. Because this is a composition as well, we can again use the chain rule, and let's try to do so with our helpful mnemonic involving blah, where blah now denotes the quantity sine x. For the derivative, we know that it will be a product, and the first term in the product is the derivative of the outside function applied to blah. Here, the outside function is the x squared function, and its derivative is just 2x, so we apply this to blah to get 2 times sine x. Then we multiply by the derivative of blah, which is just cosine x, and so in total then, we get 2 times sine x times cosine x. It's also possible to perform chain rule on the composition of 3 or more functions. For example, suppose that we'd like to compute the derivative of tangent of e to the x squared. This is a composition of three functions. First, we apply x squared, then the exponential function is applied, and then tangent is applied after that. To compute the derivative then, we can apply chain rule twice. The outermost function is tangent, whose derivative is secant squared. So chain rule says that the derivative is equal to secant squared applied to e to the x squared times the derivative of e to the x squared. Now, e to the x squared is itself a composition, so we can apply chain rule to find its derivative. For this composition, the outermost function is the natural exponential function, whose derivative is itself. And so chain rule says that the derivative of this term should be equal to e to the x squared times the derivative of x squared. The derivative of x squared is just 2x, so this last term just becomes 2x. In total then, the derivative is given by 2x e to the x squared secant squared applied to e to the x squared.